we're going to continue our Newtonian mechanics discussion, and now we're going to look at the big picture, and by big picture, I of course mean systems. We're going to start with the pulley. We've looked at pulleys. This pulley has mass now. We're kicking it up a notch. So in our old way of looking at it, we would draw a force diagram for every single piece. So let's go ahead and do that. I'm going to establish an axis for the system, and the reason I'm going to do this is so that my plus and minuses will be consistent. In other words, the acceleration of big block m down is equal to the acceleration of block little m up, so I don't have to worry about signs. Always make an axis and stay consistent with your axis. Your axis is one of the most important steps to your problem. So draw a picture, and make an axis. Very important. Don't forget that. So I draw a force diagram on each piece. Let's look at the little m first. The only forces acting on it, I've got T1 minus mg, because mg is going down, equals mass times the acceleration. Okay, that's good. We'll save that. And now I have an expression for T1. Great. Now let's look at block m. I've got sum of forces, and the m, again, we're working vertically. So ma goes over here, it's going to accelerate. mg is pointing down, and mg is pointing in the positive direction, and T2 is pointing in the negative direction, relative to the axis I established. And now I have an expression for T2. Great. What do T1 and T2 act on? The pulley. So let's set up an expression. This is a torque expression because the pulley is going to rotate. And remember, torques cause rotational acceleration. So T1 is going to pull it in the... Now we're going to jump back into Newtonian mechanics, and we're going to look at the big picture. And by big picture, I mean system approach, which is kind of nice. Because remember, when we're looking at systems, we only care about things that are external to the systems. External forces on the system cause accelerations of the system. So we have a block of a pulley. This pulley has mass because, well, you're just that good. So what we're going to look at, we establish an axis. This is probably one of the most, and by probably I mean is, one of the most important steps of setting it up. And the reason I'm setting up an axis for the system is so that I can say, oh look, if this block goes up, this block goes down, and my A's will be consistent. Makes things easier to remember. So let's draw a force diagram for each piece. Okay, and then we're going to look at each little individual spot. I'm going to start with block little m. I know that the forces on block of little m are going to cause little block to accelerate. All right, and again, I'm using this blue axis for my plus x, so T1 is going in the positive direction. The force of gravity is going down, and it causes the acceleration. Remember to work vertically. You need both parts of this equation in order for it to work. Now I get this nice expression for T1. Great. Now let's get an expression for T2 by looking at the big block. Well, here I've got T2 is in the negative direction. Why? Because that's how I set up my axis. So that the acceleration A of the little m and big M are going to be the same. And mg is pulling down in the positive x direction. So now I have an expression for T2. What do T1 and T2 act on? Well, they act on this pulley. All right, and I'm using a sum of torques equation because it's going to angularly accelerate. So I used my original condition. So I'll call this as plus alpha, just because counterclockwise is positive. And granted, this goes counterintuitive, but I'll make that fix a little bit later. So a force, tension 1, at a distance, the radius of the pulley, minus T2R2, because that's going in the opposite direction, in the negative direction of torque, causes the moment of inertia of that pulley to accelerate. So then I'm going to use what I know of the moment of inertia for a pulley, and I'm going to use alpha. Notice that negative sign? That negative sign is going to say, oh, if this pulley goes this way with T2, that is in the positive x direction. So that minus takes care of those signs and makes all my accelerations for the system along the same direction. And then I've got, oh wait, there's an R. So one of the R's goes away, the other R gets divided out there. So now I just have, T1 minus T2, that's the pulley. Now we can combine this with everything we know. So So what I'm going to do, I'm going to plug this for t1, I'm going to substitute this for t2, and I get this expression. Pretty nice. Now we're just going to group terms so that all my accelerations are on the same side. All right. So my accelerations, and again, my accelerations were in the same direction because they are consistent with the axis I established. And I get the acceleration of the system is just mg, big mg minus little mg over this mass. What does that look like? Huh. Well, this down here, that's the effective mass of the system. Remember, rotating objects contribute an effective mass, which is based on their moment of inertia. And this right here, I'll use different colored ink. I will use yellow ink, because I can. This right here is the external force. The external forces on the system are just gravity acting on block M, big M, and gravity acting on block little m. Huh, so if I look at the whole system, I can get the acceleration of the system and only have to care about the external forces on that system. That's pretty cool. Now let's look at this in a different way, and we'll start with a systems approach. So here I've got these boxes, and I'm interested on the force, the tension, right here. This is the tension I care about between blocks 3 and 4. But I know since all of these boxes are connected, if I pull this way, all of the boxes move. So we need to establish a system to find the acceleration of each block. And I'm going to make my system the whole thing. And the reason why is because now the external forces, I'm pulling on it, that's an external force, normal force, gravity pulling down on the entire system, and then this force friction. So for the system, let's start with the y direction. I know the acceleration of the y is 0, and the only two forces, I just have mass of the system times the acceleration due to gravity, and the normal force. Oh, now I've got an expression for the normal force on that system. And then mu k, let's look at the x direction. I know they're going to accelerate in the x direction. I know force of friction, and I know the force I'm applying. So now I can get, oh look, I can solve for the acceleration of the system, which is the acceleration of all the blocks. That's pretty good. And I can get the acceleration of my system. All right. So now I know the acceleration of the system. I know the acceleration of this block, which is great because this is the force I care about, that tension in that rope. So now I need to look at a different system, just this little box. So I've got the tension, the rope pulling it, and now my normal force and the mass and the frictional force that I care about are just the force on that little block. So in the y direction, works out pretty much the same way, except now it's just the mass of block 4. So now I have my normal force. Now in the ax direction, well, that acceleration is the acceleration of my system. This is in 4. That is the tension in 4, in the rope between blocks 3 and 4. And now, well, look at that. I can just solve for the tension in that rope. So the trick to this was to use the system approach to solve acceleration of the system. So we use the system to get the acceleration of the system, and then we break the system into small chunks to find the piece I care about. So system approach to find the acceleration, then look at an individual little piece. I hope that helps. If you have any questions, please ask, and I will see you in class.